Welcome back. In this lesson we are going to discuss the out of bag error. So in the last lesson we discussed bagging, and we discussed that bagging is bootstrap aggregation, right? And we said that in the next lesson, which is this lesson, we are going to discuss the out of bag error, or how we can calculate the test error in bagging. Okay, so as you can notice, the samples can be duplicated, right? So the same sample here can be used again here, and then used again here, and then used again here, and so on, right? So the out of bag error addresses this problem. How? Using the out of bag error, the mean prediction error on each training sample is calculated using only the model that didn't have X, or this training sample, in their bootstrap training set. Okay, so here we have training sample X, right? This one. Okay, and when we test the accuracy of this classifier, okay, so in order to measure how good this classifier is, and so on, here we have some examples from the training sample. Okay, so let's say that we have 100 examples, just like here, right? If you remember here, I had an example here, right? So this is the first sample. So the out of bag error will be calculated for the samples 4, 5, and 7, right? Because these are the samples that are not in the bootstrapped sample. Okay, because when we use resampling with replacement, some of the examples in the original training dataset are not in the new bootstrapped samples. Okay, so this is called out of bag error. Okay, so there is no need to use cross validation or hold out samples in order to get an unbiased error estimation, because in bagging the error estimation takes place internally. So this is called out of bag error. So as you can see, this is the training dataset, okay, and we created this sample, right? So we created this bootstrapped sample. So as you can see here, this bootstrapped sample is now the training dataset. Okay, here this is the training dataset, or the bootstrapped sample, and the rest of the training set is used for prediction. Okay, so let's take a look here. For example, here we have 2 examples in the training set, okay, or in the bootstrapped sample, and here we have the rest of the original dataset. We use them for testing. So let's say that each square will be classified the same, right? So this square is red, this square is green, this square is red, and so on. So how many misclassified examples we have here? We have this green, it should be classified as red, and here we have these 3 reds, they should be classified as green, right? So in this case, the out of bag error, we have 15 points in the test data, and they are not in the training data. Okay, the model misclassifies 4 out of these 15. So in this case, the accuracy is 11 over 15 times 100, or basically 73.3. So this is how we calculate the out of bag error. So we can say that the out of bag estimation is nothing more than the mean estimate of the Bayes algorithm on these around 37% of the inputs that were left off the training. Okay, so again, the out of bag error idea is very, very intuitive, very easy to understand. Here we are doing resampling with replacement. Okay, so some of the examples are not in the training dataset, okay, in the new training dataset for each classifier. So the out of bag error for this classifier will be different from the out of bag error for this classifier. Okay, because the duplicated examples here are different from the duplicated examples here. Okay, it's a random process, and therefore the examples that are left out, or the difference between the unique elements in the training sample, the original training sample or the training dataset, and the new bootstrapped sample here, this is left out for testing, the first classifier. and then the subtraction or the difference between the training sample, original training sample, and this bootstrapped sample is the test dataset for the second classifier. So basically these new datasets that we got from the original dataset are used for validation, okay? Because of course we have the test dataset, we don't really touch it, we don't really do anything on it, right? But if we want to see how well this classifier is doing, then we use the out of bag error. So this is the idea of out of bag error. And let's also discuss something else, which is variable importance measures. So bagging improves prediction accuracy at the expense of interpretability, because when we were explaining, for example, the KNN, or when we were explaining the decision tree, the models themselves, the machine learning models, were very easy to interpret, okay? But the prediction accuracy was not that high. Here, the prediction accuracy will be much higher, but at the same time, they are not really intuitive, or they are not really easy to understand as the other algorithm, right? So for example, if we use the bagging idea with the decision trees, it's no longer clear which features are the most important one. So we calculate an overall summary of importances using variable importance measures such as the Gini index we discussed before, or the RSS, okay, which is short for residual of sum squared. So we calculate the residual sum of squares for regression and the Gini index for classification, okay? So this is how we can know what are the most important features. Now in the next lesson, we will see a slightly modified bagging algorithm called the random forest, and this is one of the most famous machine learning algorithms, but you wouldn't really understand it unless you understand what is bagging, okay? So bagging by itself is not actually used that much. Random forests are actually used much more than the bagging by itself, right? But in order to understand what is random forest, we need to understand what is bagging, okay? So we will understand first what are random forests and what they represent, and then we will implement the random forest from scratch. And by doing so, we will understand better what is bootstrapping and what is bagging, and how we can calculate the out of bag error, and how we can use our decision trees that we implemented in the previous section. So let's go to the next lesson.